Yeah, welcome to this session. This is a session in the internet workshop on wavelet via matrices and applications in signal and image processing. I have the pleasure of contributing to this area. And since I have been working on wavelets in a concrete and also very abstract way in the last, more than 30 years since they exist, I'm probably a person who can tell you a lot about these things. So strictly speaking, I will not talk about wavelets, but more about time frequency analysis, but I will also try to explain to you what the difference is. I have put together in a rather fast way various things, so maybe the order in which things come is not too well organized. So when I was starting to prepare this talk, I had in mind to tell you about function spaces. I like function spaces very much, and I've used them a lot over the last years. And nowadays I'm thinking there's a big zoo of function spaces, and we don't use in mathematics something like consumer reports. But I think it's a valuable idea that given the large number of such things, we would like to know which one is the best space. Because in reality, or my personal experience was that if you look at the classical spaces, then you have the LP spaces. So yes, I can look at the literature. I see that people are proving results for L1, L2. That's certainly important. Then for LP, then for Lorentz spaces, Orlitz spaces, weighted spaces, and more funny spaces, but they're just getting, to some extent, more complicated, whereas nobody is considering the question, which of the spaces is useful? And then, of course, you have to ask, for which purpose? I mean, what is the best car? The answer depends on whether you look for a family car, whether you go through bed or streets or highways and so on. So I think it's a good idea to know how to orient yourself in the world of function spaces. Now, it's plausible or clear if you see this picture that you know what L1 is. These are the integrable functions. And you know what L2 is. These are the square integrable functions. So that's the yellow object. When I'm using these symbols, the idea is that every symbol representing such a function space is inside of another one if it's a smaller space. So here you see the blue part is L1 functions which are not square integrable. So these are functions which are having such big narrow peaks that if you square them, they are not integrable anymore. And of course, there are L2 functions which are not L1, like the sinc function, sinus pi x over pi x. It's decaying like 1 over x. It's not integrable, but if you square it, it's integrable because 1 over x squared is integrable over the interval 1 to infinity. Now, I also use this picture to demonstrate that if you have a Fourier transform applied to such a space, so from the blue object you get the red object, then you're inside C0. So green object here is C0, continuous complex values functions vanishing at infinity. So the Riemann-Lebesgue lemma that you learn in Fourier analysis is the red rhomb is inside the green rectangle. Now, I like to work with what I call a Banach Gelfand triple, which is a triple consisting of the Hilbert space L2 in the middle and the space S0, also known as Fichting algebra or amalgam space. It's a particular Segal algebra and its dual space. So what you see at one stroke from this picture is everything that you are doing normally is inside S0 prime. And on the other hand, S0 is inside of this universe. Now, the idea of mathematics is, of course, not to make all the time things more and more complicated, but to allow things to get more simple. So for me, the ideal world is the Banach Gelfand triple with this setting. And very often when I'm teaching, I'm saying this is like the numbers. I mean, what are numbers? You don't need a philosophical definition of numbers, but you should know how to compute with numbers. And then we have the rational numbers, which are very convenient to do multiplication. You have 3 over 4, you want to get the inverse, you write simply 4 over 3, you are testing it, denominator and so on, and you multiply it out. It's clear it's 12 divided by 12, which is 1. So strictly speaking, you have equivalence classes of pairs of integer numbers with non-zero denominator and so on, but we know how to compute with them. But then we realize that there is nothing like a rational number which has a square which is equal to 2. So square root of 2 is a real number which is not in the rationals. So the world of real numbers is like the L2. We're completing the space which is nice, but too small to get a Hilbert space. But then we are left with the problem that not every quadratic equation, okay, sorry, thank you. Oh. So are you, I hope you can see now. Yeah, okay. So I go back, the first slide was this one with all these function spaces. And then now we are having the Banach Gelfand Triple. So the outside is like the complex numbers. First you're saying, well, imaginary unit, you don't know if it exists, or engineers learn there's a delta, but it's not really a function, but you can work as if it was a function, but it's very useful, so we handle it. Now, when you think of something like the relationship e to the 2 pi I equal 1, that's really happening in the complex domain. And despite the fact that e is irrational, you have a complex exponent, it's really meaningful. So it's good to know that we have 3 levels of numbers, or here we have 3 levels of functions. The first one are the good functions, where even the Fourier inversion theorem is working properly. Then you have the Hilbert space, where you can express the orthogonality relationships. And then you have the big space of generalized functions. But actually, this is the space where you have, for example, the audio recording of my voice. It's not really a function, but I can show a spectrogram and I can work with it. So it's definitely the world that you would like to have. Now, most of you probably are familiar with the Schwartz space. So the Schwartz space is the dual space of the space of rapidly decreasing functions. So inside of the zero Segal algebra, you would have the space of rapidly decreasing function, and the dual space is the space of tempered distributions. Now, the space of tempered distributions is not so simple, so that's why I made this curly object. But of course, if you rotate it by 90 degrees, then you would have an invariance property. So essentially, I would say we could define everything in the world of tempered distributions, but this is not the main point or not the main focus. Now, there is also, without giving too many details of what are Banach Gelfand triples, it's clearly they are triples of spaces. There's a small guy and the big guy, and the Hilbert space is in the middle. You can also start from the Hilbert space and say it's decorated. It's a so-called rigid Hilbert spaces, and that's the terminology used mostly by physicists. And I would say it's a Hilbert space with extra structure. Now, if you remember that every abstract Hilbert space, a Hilbert space is a space with a scalar product, you take the separable Hilbert space, and the prototypical example is just L2, the square summable sequences. And we all know that inside of L2 you have the summable sequences, and the dual space of L1 is L infinity, the bounded sequences, complex valued sequences. And important fact, L1 has a dual which is exactly L infinity. L1 is a dense subspace of L2, but L2 is not dense in L infinity. If you take the closure of square summable sequences with respect to the sup norm, you will just get C0, the space of sequences tending to 0 at infinity. So that's why one should look at L infinity with two structures. It's a Banach space with the sup norm, but it also has coordinate-wise convergence, which means that you're testing your convergence against the unit vectors of L1, but you can also take arbitrary elements. And this is why weak star convergence is coming in, but this is for those who like functional analysis. Now, maybe because we're talking about Fourier analysis, you remember that the classical approach to Fourier series tells you that a function which is periodic can be identified with an L2 sequence of Fourier coefficients. And it was Norbert Wiener who was suggesting to say, well, those who are corresponding, which have Fourier coefficients in L1, we call this the space of absolutely convergent Fourier series. And then people in distribution theory took the dual space and they said, well, we'll call these pseudo measures because it's larger than the space of measures. But this is for me the prototype of a Banach Gelfand Triple isomorphism, just to use this word once in this talk. It's just saying that if you have two such objects, and if you have a mapping which maps the Hilbert space into the Hilbert space, it restricts to the small guy, but it extends in a unique weak star continuous way to the big guys, then you cannot distinguish these two Banach Gelfand triples. And so what I was doing, or what my insight was over the years, is if you try to do the same thing inside of L2, you should not take the Fourier algebra, but you should take a 0. That's the right analog for L1. And there are so-called Wilson bases, which are a little bit like wavelet bases, where you can even establish such an isomorphism. By the way, I would like to mention that these Wilson bases were used by the physicists who were doing the LIGO experiment to detect gravitational waves. So there's a very strong connection to, the Nobel Prize in Physics from 2017. This is just put together a number of papers I have written in the last few years, more or less in order to promote these general ideas. For example, choosing function spaces is a paper where I tried to give a hint how we could talk about consumer reports and what are the construction principles for different function spaces. So there probably you can learn a few things. Then the novel approach is that I was saying that engineers are interested in convolution and Fourier transform because they want to describe the translation invariant system as it is appearing in engineering by a convolution operator. And the convolution operator can be turned into multiplication operator. This is where the terms impulse response and transfer functions come in. But usually in the engineering literature and even in many books, this is a very vague and shaky ground. And I try to give this a simple mathematical explanation. So essentially I'm saying one should start by discussing the continuous bounded linear operators from C0 to C0, which commute with translations. Later on, then I realized that I can even do many things which are done a little bit cumbersome in classical Fourier analysis. And I call meanwhile the dual space as 0 prime the space of mild distributions. So every mild distribution is a temper distribution, if you're familiar with it. And in this setting, you can do a lot of things from classical Fourier analysis. For those who are following this course, maybe this article about Gabor expansions might be interesting. And in order to demonstrate that we can do this kind of distribution theory, only knowing Riemann integrals, I was writing this article together with Mats Jakobsen. This is still in development. Another idea is the idea of sequential approach. If you do distribution theory, there is the approach by Lighthill. So instead of talking about the dual space of a nuclear Fréchet space, you're taking sequences and you're taking equivalence classes of sequences. Now, the difficult thing in the Schwartz setting is to prove that if you have some equivalence classes of nice Cauchy sequences of nice object, that you really get a continuous linear functionals. There you need a lot of functional analysis and topological vector space theory. But in my approach, I need just basic results from linear functional analysis. So these are some of the papers that are interesting for you, and you find all the information at this web page or on YouTube, but that's just kind of advertisement. Now, I realized that, or I've heard yesterday that the participants of this talk are mostly people teaching engineers and some form of mathematics. Now, there are a lot of things that I could share with you. And for example, that Fourier analysis is a very good object to tell young people how important abstract mathematics is. Because every young person has now a mobile phone. We're doing this talk through internet. So digital information is moving from one place to the other. You see my slides, you hear my voice, and all these are signals which by the help of mathematical methods are compressed, sent through the system to either channels or mobile communication to the receiver, are displayed in different formats, maybe in a small screen or a big screen. There's a lot of mathematics behind it, very often related to things like orthogonal systems. Think of images which are compressed with the JPEG methods. That's just a nice orthogonal system in the background, which allows to compress images by fixing for 8x8 pixel images a fixed orthonormal basis with 64 building blocks. And when you transmit and you have not enough capacity, you're just transmitting maybe the first 20 of these coefficients, and the user, the receiver, knows how to put them together. There is no redundancy built in, because if you have an orthonormal system, there is no linear dependency. So you can do a lot of things by just translating abstract concepts from linear algebra, for example, and I would say also from functional analysis, into this real world. So this slide was more or less prepared at the time when I was still thinking to talk more about these function spaces. But you see there are various questions, including the questions of which space should use for which purpose. And of course, there is something like a learning curve. If you have a very complicated function space, which is only good to solve a very particular question, you might not be, or the broad mass of students might not be willing or able even to study such spaces. So I realize that we have certain spaces which are universally applicable, not too difficult to understand, and still very useful. I also like to compare the situation with mobility. So for a long time, it was important to say, we have to learn, engineers have to know how to build cars. And building cars may mean to build a strong motor, to have all the details of a standard car that we have now. More and more we learn that we don't need cars, we need mobility. Maybe an electric car, maybe a transport system is what we should know in order to efficiently solve the problems of mobility or so. So I think for me, the LP spaces are a little bit like the standard cars. Everybody is using them, but nobody is asking why we should use them, or why we could solve, how we could solve the problem otherwise. Now I will talk a little bit about the difference between wavelet and time frequency analysis, because I think that is important for your orientation. There is a very nice paper by Dobschi, Grossman, and Meyer. Yves Meyer once said, it's a painless paper. He had not to do much, just share a few ideas, and I think Ingrid Dobschi, a young person at that time, was writing the paper with the inspiration of the senior people. Alex Grossman passed away last year, I think. But it's there you see that wavelets and short-time Fourier transforms are really coming in a very similar way. Whereas meanwhile, wavelets have a lot of publicity, so to say, whereas time frequency analysis is only now in the last maybe 10 or 15 years catching up. So the wavelet wave was really going strong from the late 80s to the maybe the first decade of this century, whereas in the last 10 years, people were moving on to topics like compressed sensing and many other things. So these are just further illustrations and indications of the early papers, because the Balian theorem was a result saying that in the context of time frequency analysis, one could never get an orthonormal basis of time frequency shifted elements. That was the motivation by Yves Meyer, as he told me personally, to try to prove that the same thing is true for the affine case, until to his own surprise, he found out that orthogonal wavelets can be constructed, and meanwhile we have a huge number of such orthonormal wavelets, and they are very useful, and everybody knows, of course, how to use them. There's another aspect of this story. Wavelet orthonormal systems are very good to characterize function spaces, and those function spaces were already used for Calderon-Sigmund operators, so very important objects generalizing something like the Hilbert transform. On the other hand, the function spaces related to short-term Fourier transform only came up or became more fashionable in the last 20 years. Also, I've introduced modulation spaces already in the 80s, and I can say that I was presenting them more prominently in 2003 at a workshop or a conference on wavelets organized by Professor Rada in Chennai. So that's where modulation spaces really were reaching popularity. So meanwhile, you have these papers here, and in the year 2020, even two books appeared, one by Arpad Penny and Kazuo Okuchu, and the other, I think it's available soon, is by Elena Cordero and Luigi Rotino, who are showing how they can be used. So just to make the connection, S0 for me is the prototype of a modulation space. And S0 prime is another modulation space. And all the spaces in between M1, as it's called now, as S0 is called in these books, are the MP spaces. So the MP spaces are for time frequency analysis probably more useful than the ordinary LP spaces. I've failed to add the book of Charlie Gröchenig on foundations of time frequency analysis, but probably you find them somewhere else in the slides. Now, what is the difference and what is the analogy between time frequency and wavelet theory? Well, you have always a continuous transform, you have a continuous wavelet transform, or you have the so-called short time Fourier transform, and there's a group in the background. So you're testing your signal, your voice or so, against transforms. Now, in the idea of wavelet theory, you have constant shape. Well, how do you preserve the shape of a function, of a building block, a wavelet? You are moving it along the time axis, or in 2D along over the visual plane, and you're dilating it. So you're stretching it, and you have short wavelets, long wavelets. And because you have very sharp peaked wavelets, you can represent edges quite well, and that's why the wavelet transform is really good for compression. On the other hand, so it's the action of the affine group. Substitutions of the form f of x goes to f of ax plus b with a positive x, the dilation parameter, and the shift parameter b is what makes the whole system of continuous wavelets from a single Gabor wavelet. Now, the art was, and still is, to find the right construction and the right lattice, discrete lattice. So typically you take shift by integers, plus and minus natural numbers, and then you dilate everything by powers of 2, positive and negative powers. So in this way, you're producing a kind of sampling set, a sampling set that allows you to create an orthonormal basis. Recall that the difficulty is to have a system which is rich enough to generate all the L2 functions with square summable coefficients. On the other hand, you have to have all the orthogonality relations, and that was not clear that you can do it. Now, in the case of the short-term Fourier transform, the situation is different because whatever you're doing, either it's a nasty simple rectangular function, or if you try to do it with a smooth function, for example, with the Gauss function, as Danish Gabor was suggesting in 46, you would never get an orthonormal basis. You would not even get a Riesz basis. So whenever you have such a nice building block, either you cannot represent every element, then you have a nice, if you're lucky, a nice linear independent system, or you're representing everything in a stable way, but then you have linear dependencies in a way, not in the linear algebra sense, but you can throw away one or even infinitely many elements and still represent the rest with no real problem on the coefficients. So that's why I would say that we were forced, I was working more on atomic representation with the short-term Fourier transform, which is what we call Gabor expansions. You're forced to try to understand what frames are. These are the redundant systems which are not orthonormal basis, and we have to do these things. Now, the abstract viewpoint is captured in the work of Charlie Gröchenig and myself on what is called co-orbit theory. So, co-orbit theory is a theory which says, well, you have this group action, and think first now of the wavelet transform. You have shift and dilation, and you have your Gabor, your wavelet, and you're doing continuously a correlation, a scalar product in your Hilbert space. So normally that will be L2 with these atoms. And then you have the short time, then you have the continuous wavelet transform for the X plus B group, or you have the short time Fourier transform for the Heisenberg group. And then the question arises, well, if you're sampling properly, maybe dense or sufficiently dense, maybe along a grid, maybe along a discrete point set, which is just dense enough, can we reconstruct? And the joint property is, if you're starting with good atoms, so for us, for time frequency analysis, this is just decaying property and smoothness. For wavelet, you would have an admissibility condition. You can give me any decent function, so maybe any function which is a candidate to be a wavelet, and then you could give me a dense set, even if it's irregular, I would be able to show with the help of co-orbit theory how to get a representation of this form by making a dual frame of this family. So that's the terminology, but I would like to go then to more concrete things. So I would like to mention that for the case of time frequency shifts, it would be okay even to get an orthonormal system, but take the rectangular function, which is just the function constant 1 on the interval from -1/2 to +1/2. If you shift that function, you get an orthonormal system, but even if you do Fourier analysis over each of those pieces, you get a complete orthonormal system. But if you have a nice bump function living maybe on the interval from 0 to 1, if you decompose it into this system, you have not even summable coefficients because you cut that bump function into 2 pieces and you get a huge number of coefficients despite the expected smoothness of the object. So this is related to the Balian law principle. So I will show the demonstration in a moment. So sorry for this abstract introduction, but I would say elements that we need for the time frequency analysis are called Gabor families, and we have to decide whether we want to represent functions. Then we are talking about a Gabor frame, or we are trying to communicate. Mobile communication is using Rees basic sequences. If you take the modern mathematical terminology, it's just, I would say, linear independent vectors where the receiver knows that I have sent through the electromagnetic world some linear combination, and then of course by taking the bi-orthogonal basis, she or he can pull out those informations, those coefficients. So a frame in this terminology from the linear algebra point of view is just a linear spanning system, and a linear Rees basis is a generating family. And the basis, we would say the elements, the columns of an invertible matrix, they're a general basis. You can also say they're a distorted version of an ordinary basis. This would be the combination of these two concepts. So a stable generating system with uniquely determined coefficients, that would be a Rees basis, but time frequency analysis shows you cannot have such a good thing. Again, I've collected some of these things. Now, the next part, the main part from the rest is, I would like to demonstrate to you a few things, how I'm working, and clearly it's background for the abstract stuff, but I'm doing a lot with MATLAB, sometimes just to say, well, I know how to do Gabor analysis in the setting of locally compact abelian groups. So you can do it for the real line, for image processing, I can do it two-dimensional, but I can also work with pixel images, or I can do it one-dimensional. That's what I will demonstrate to you. So I will use MATLAB, which is matrix laboratory, it's not mathematics laboratory, MATLAB to do linear algebra, and I have a toolbox to do this. Sometimes, so I demonstrate concepts of linear algebra, or I'm using linear algebra via MATLAB to do things. I would like to use it for illustration. So actually, the pictures I have shown you about these function spaces are just polygons or figures in the complex domain, and with the cfill command, I was filling them. So I was using MATLAB to produce these pictures. Now, I'm also using MATLAB quite a bit for teaching, and it might be interesting for you. But also sometimes I want to solve a problem, and then I would like to do a numerical approximation. The good or important thing is, if somebody says, I would like to do a numerical approximation, then you would like to know how reliable is the result of my numerical computation. That's another place where you need function spaces. So recall, we have the nice Riemann integral, which allows you to find the integral of a continuous function. Now, this is good, universal, and robust. So whatever continuous function, even if it's a very nasty continuous function, if you work very, very hard and you take millions of sampling points, then finally, eventually, the Riemannian sums will be okay. But most people would say, no, I have just a very simple function here, maybe a polynomial of degree 5, and I would like to integrate it. And then a trapezoidal rule or any other rule is much more efficient, and you would like to know how to do it efficiently, and you would like to have a guarantee, and that's where mathematics comes in again, that with certain assumptions on the smoothness of the underlying function, you can guarantee a rate of convergence of trapezoidal rules, which is much better than step function approximations, even for nice functions. And so that's kind of my idea of conceptual harmonic analysis. Conceptual harmonic analysis is combining abstract harmonic analysis, which allows to do these things, I mean Fourier analysis for discrete periodic, discrete non-periodic, continuous, multidimensional, periodic, and so on, FFT, discrete Fourier transform, always on different groups. but I would like to use FFT to compute the Fourier transform given by an integral. And even for a generalized function, I would like to be able to simulate things and explore things to find out what kind of theory is reasonable and what kind of theoretical expectation is nonsense, because already a simple counterexample displayed to the students tells them that you have to be careful with certain things. I must also say that I'm using GeoGebra quite a bit nowadays for demonstration. Unlike MATLAB, where you have FFT built in, and you can do matrix manipulations, matrix inverse, pseudo inverse, which I think is extremely important. You can load images, you can handle voices, and all these things. So it's kind of a practical engineering tool, whereas GeoGebra is a very good, nice teaching tool. And in GeoGebra, you can start to demonstrate the properties of matrices and so on. So I'm not sure if there's enough time at the end, so I will jump quickly and just show you pictures. But it's also for, you can design such things very easily yourself, just knowing the mathematical content, and then share it with your students. I think that's another good idea. So this is a small file demonstrating the Lagrange interpolation problem. So clearly you see a bunch of cubic polynomials, and they are going through 3 points. They're just the points 1, -1, +1, and 3 here. And you see some slides. So that allows you to change the position of the points. And these polynomials are made, let's say the red polynomial is a polynomial which is having 3 zeros, but as particular value at this point. So I was just right. You see a p of x, yeah, maybe a cubic polynomials, so they can have 3 zeros. So the p of x you can read is x minus 0, so it's just x. Another 0 at +1, another 0 at +3. So the p of x, you can show it also, is just a product, and then you have another polynomial which is it should have the value. You see 2 is missing, so I would like to have a Lagrange interpolation polynomial. So just divide by the value of p at 2, and it turns out to be 8. And then you can take these points, you move everything, and the whole construction is changing. So this is a very good thing. So sorry, this comes twice. Another thing which I found quite instructive, even just for myself, is a small demonstration of what the bi-orthogonal system is. So the idea is very simple. In order to show to the students how you can understand the vectors which sit in a 2x2 matrix, so this is the matrix H, I was demonstrating it by taking 2 vectors, these I think it's the red vectors, which are sitting on the unit circle. So the construction is make a unit circle, make 2 moving points, and take the vectors as column vectors of a 2x2 matrix. Then the HI is the inverse matrix. So I was just doing a simple computation. And then I want to show you, and that's the interesting part, what do you know when you multiply an inverse matrix with a matrix? That is the product of the 2 matrices, but this is the scalar products of the rows of the inverse matrix, the columns of this. So I have to show you now the rows of the inverse matrix, and these are the black guys. And I was surprised for myself that it's very easy to understand what you see here. I mean, the construction is that they have to be bi-orthogonal. So the guy who is in the second row has to be perpendicular to the first row. So this is why it has to be perpendicular. But when you project in the direction of the other one, the projection should be 1, and that means I was solving this problem by saying, well, you're taking a kind of harmless construction in this way, and you can change now, and then you start to move the points. So here the frozen picture is that this is an acute angle, so it's smaller than 90 degrees, and you see the bi-orthogonal vector is larger. And so then you make it smaller and smaller, the bi-orthogonal system will be bigger and bigger, and then you cross it, and then you make that bigger. And of course, it's a symmetric relationship. The inverse of the inverse matrix is the original matrix. And then you would see that the matrices which are self-bi-orthogonal, you know, these are the unitary matrices, are exactly the ones where you have 90 degree, where the original system is the same as the other system, but you have to go from rows to columns. And that means the definition of a unitary matrix is take the matrix, take the transpose of the matrix if it's real, or transpose conjugate, and you get the inverse matrix. So it's a very nice tool to demonstrate things. Recently, I was asked to look at a paper on Ries products, also going back to Frederick Ries. And I thought, well, I would like to see how these functions look like. And you type in f1 of x is 1 plus cosine of 3x. And then the idea was that you take cosine functions with quickly increasing frequencies. So I just typed in the three things. And when you type in here, you can really say, I type h equals f1 blank f2 blank f3. It is displayed as h1 is this. And then you see the graph and you see, oh, that's an interesting function. Can I study it? Why does it have nice properties or so? So it's one of the things where I'm using these tools. And now I will switch to I hope it will work, to a new screen. That's also something that I learned more or less recently, how to deal with the MATLAB. I'm not sure. I think you will probably now see my MATLAB screen. So yeah, I think you will see the MATLAB screen, but I should look for another one. Yeah, the live editor. Yeah, please feedback. I think I got the feedback. So do you see this line which ends with redundancy? Okay, great. So what I would like to demonstrate, and as I said, I only learned about the use of the live editor relatively recently, so I hope I'm doing it properly. So what I will do, and what I try to do, is that I will show you by pictures what what a Gabor family is in a discrete setting. So I'm moving now to a situation where we are talking about, on the one hand, linear algebra, but on the other hand, signal processing. So we're talking about the signals of length 480. I'm using this because it is a number which has a nice collection of divisors. So, you know, in the case of integers, every natural number is giving you a lattice. If you have n equals 512, you have a very fast FFT, of course, but the number of divisors, just to show you for comparison, that's a private, easy, simple command of even, I don't know, 1024 is not so rich, because you have only other factors of 2. So 480 is a number which is quite good. Maybe hope it works also here. You take the number of samples that you get from your HGFei instrument, and you see it's a long list, not even visible completely here. So you have 79 divisors. So actually the prime factorization is 44,100 is 2 times 3 times 5 times 7 squared. So that's an interesting side remark for mathematicians. Now, we will use a time step, which is 20, a divisor of 480, and a frequency gap, which is 16. This is in order to demonstrate the effect of different time gap in the time and frequency plane. And if you're asking, we will see it in a moment, how many lattice points such a lattice has, then you will find out it's 720 lattice points. So we will work with 720 Gabor atoms in a 480 dimensional space. And that's the quotient with the redundancy is 1.5. Now, Gabor in 46 was saying we should take the Gauss function, and I'm taking the discrete Gauss function built in a particular way. And if I plot it, the plot looks like this, which is kind of maybe not exactly what you would like to see, because you would like to see a picture like this here. Now, this is again important warning. Some engineers are suggesting to sample a Gauss function from, I don't know, -5 to +5 in order to have a plot like this. But if you take the FFT of that sequence, you get a crazy object, because you should say, no, the Gauss function is a function living on the real line. As a mathematician, you know it's an even function with the 0 in the middle. And now you have to wrap it up on the unit roots of order 480. So more or less you plot it on a cylindrical object. And that's why you should start with 0, and that's the peak value. And you go down, and then on the other hand, so to the left of the 0, you have these values. And if you would do it with a small number, you would see that the peak value is only appearing in the peak at 0. So you have bookkeeping problems, like the first MATLAB component is the value at 0, and so on. I don't do it here. Or maybe I add something like this, plot num unit roots of order 8. I'm not sure if it will work, but let me try to. No, it's not showing up in the right place. Oh yeah. Yeah, here it is. So the unit roots of order 8 are, of course, the multiples of 45 degrees. But in the MATLAB order, if you have a function living on those unit roots, you have to see that the order is this one. So if you have a discrete vector, you should think, normally in a mathematical terminology, it's quite easy. It's x0, x1, x2. But in MATLAB, you have to take a first, a second, another coordinate. What is an even function? Of course, where the value at 2 is the same as at 8. But the first one is untouched. So you have to be careful when you go from continuous to discrete. Now, what we are doing is we have time shift, which means we're doing an offset of this. Maybe I'll make it a little bit smaller. We're doing an offset to the right. And of course, this has to be done in the spirit of a cyclic shift. Or we multiply with a pure frequency. So this is something which has a certain number of oscillations on the full unit interval. And this routine is showing you the Fourier transform. So the effect of a shift is a multiplication with a pure frequency. A multiplication with a pure frequency is a shift on the frequency side. So these are the objects that allow us to build these things. Now, I also put something like this here, meaning that I'm not sure. It's hard to I think only the scaling of figures is, yeah, now it's better. So if I show you a filter, then it should be something which is arranged around 0. So you would say you're sitting at 0, and the 0 component, let's say, is the first MATLAB component. And then you would like to do a filter which lets through everything which has a maximal frequency of 20. That means you would put 20 ones to the right and 20 ones to the left. So in the MATLAB system, you would have at 0 plus 20, which means 21 zeros here and 20 on the other end. And you see here, it's not good aligned. It doesn't end at 480. It's going the peak value. So I have my own plotting routine, which does this plotting automatically. It puts some boundary or so. So that would be a picture of a rectangular function. And of course, you can take the plot of the FFT of that filter. Maybe I'm adding this. I'm not sure if it will work right away, but plot set the FFT of the sinc function, of the filter. And we should be able to see such a discrete sinc function. Here it is, yeah. Okay, so this is the Fourier transform of the rectangular function, but you have to see that the data structure has to be correct and the plotting routine has to center it. Otherwise, you would again see something going down. I mean, we can play quickly and change it and do it once more. Now you would see kind of nonsense because it's a complex valued function with an imaginary part which is spurious. So you have actually a real valued function by rule. So that's why I can also change it one more time. And then you say, well, no, I would like to see the data structure. And then you see the imaginary part is tiny, so it looks like 0, which it should be. And then the real part is like this. So the data structure is showing like this. But if I go back, the centered plot is showing you a sinc function as you would like to see it, but one has to be careful with this. Now we can do the same thing in 2D. And there we have, I did just a Gauss function with 12 pixels. And then I did for display a Kronecker. So a Kronecker means you take a block matrix where each block is now this tile which is going from here to here only. So you see that would be the tile displayed in a naive way. That would be the tile in a good way. So essentially you would say, yes, everything is supposed to be periodic, and I cut out such a part here. Now, if we do a short-time Fourier transform, and we take a Gabor family, these are Gauss functions. And Gauss functions mean we have in a TFT picture high concentration. So the number 3 is just you're moving first down at a fixed position in frequency. And of course, you're coming back here. Or you're taking one of the later numbers, then you're already at another position. And you have a very high frequency, but you can also say it's a relatively low frequency, which is coming from the negative side. So these are the building blocks that you would have. So if you take such building blocks, Gaussian envelopes multiplied with frequency, you can get this. Now, the discrete version of, yeah, maybe you see it better here, of a random signal. So for me, it's row vectors, and I take the short-term Fourier transform really by computing 480 Fourier transforms and plot them as columns of a matrix and show the picture. Then this is the picture. And if it's a random signal, you see there are a lot of deep values. So these are well, you see the absolute value of the short-term Fourier transform. And now the idea is, well, if I do a good sampling pattern, and we have here 720 points, then you should be able to reconstruct from these points. Now, I have a comp-norm routine, which is just saying, well, you can compare let me see if I can get it better. Yeah, okay. If you have two things which are have the same number of entries, then hopefully you can compare them. And if they are not having the same size, you divide through. So what is the first part? Well, I was computing the index sequence, which is the sequence of all the coordinates of our lattice. So I'm not sure if I have the lattice, but let's say you go down in the frequency direction with this lattice constant 16, which is our B. So you start at 0, which is MATLAB 1. Then you go down plus 16, plus 16, plus 16. And then you're jumping, and after a while, you're getting further, you're jumping to the second row and so on. So we are really saying you are going through this short-term Fourier transform. This is sampling point number 1, 2, 3, 4, and so on. And then, of course, you go down this, it's just by display. And then once you're done with all the first column, then you're doing this here. The second column is starting here, 1, 2, 3, 4. So we are reading out from this continuous function, which has n squared samples, we're reading out the values. Or we are building the Gabor system, which means if you give me any point, I would say, oh yes, this is something which has been shifted by 3 times A, no, 3 times A, and modulated by frequencies, which is 2B. So at this point, I have a time frequency shift operator, and I put all these 720 elements together, and I take ordinary scalar products with my random signal. And then the comp norm routine says, well, these are the same data. So in linear algebra, you would say, I have a bunch of vectors, like 5 vectors in R3, and I try to reconstruct my vector from those 5 scalar products. Or I'm saying I'm having a continuous transform, I mean pseudo-continuous. We have a picture, and we sample the picture at the same number of points, and of course we have to take care of these things. Of course, at the left side, we were computing a continuous, and we're sampling, but we can do it in a fast way as well. And then the answer is, well, in linear algebra, you would say the minimal normally square solution for this problem is using the pseudo-inverse. You can do it in 2 ways. Either you remember I'm using row vectors. So when I do x with pinf, I'm computing a set of 720 coefficients. Maybe you would like to see it in this way. And then you're computing the minimal normally square solution that allows you to represent the x with the cheapest coefficients. And in reality, I'm using the dual frame if you do frame theory. Or somebody is saying, and that was what we had before, I have the samples of the short-term Fourier transform, which is the same as I have the collection of scalar products, and I would do the synthesis. Now, with these demonstrations, you can say, well, I just want to look at the pseudo-inverse, which is the first row of a vector of a system of the same size. And it looks like this for our given situation, which is quite typical. Oh, sorry, I was distracting. Yeah, okay. And yeah, I think I'm now at the end. Yeah, maybe I should. Yeah, I just did the computation here. So the key point is, from a linear algebra point of view, that if you take a Gabor system and you do the computation of the pseudo-inverse, then you can also take the first element and you can have routines to compute it in a fast way and recreate a similar system. So I do the same modulation shift along this same 720 points in the frequency plane. And then the comp norm routine tells me this is what we would get. So whereas normally people say it's a cumbersome thing, we have a frame operator and a system which is not an orthonormal system, so we have to invert the frame operator, and that's cumbersome. In the case of Gabor analysis, we can do it in a very simple way. And maybe I can try to show you only 2 more things. I'm not sure if it will work. that will be SPI-SLAM. That would be a way, here to show you my collection of points. So you see these are the points in the plane, and actually I want to show you the axis. So I have to run it once more. So this is the collection of points, but I also have another way to do it. Subplot 1-to-1 and spice. I can modify it, the lattice, to get an oblique lattice. So it doesn't have to be a rectangular lattice. That's one of the nice stories of Gabor analysis. Then you would get such a lattice. Again, maybe I should plot X. And sorry, run it. So this is one of the nice things that you can do. You can say, well, any such family, it will be a Gabor frame if and only if you get something like, you can create every element, and if you can do it with a pseudo inverse in MATLAB, but then you would like to know how it's working. So I think that's more or less the story I would like to tell you. I only try to see if I can show you at least one of those GeoGebra files, but I think it's too cumbersome. Yeah, maybe I just take this one just to show you how you can use it for LiveScript. So this is a demonstration showing, that's also for linear algebra courses, how circle, how vectors are changing under a linear mapping. And so I have a matrix written somewhere here. It's just a harmless matrix, 1, 1 in the first column, 0, 1 in the second one, but of course you can change it. And then I have a circle. So if I have points in the circle, you can see how the vectors, you can think of vectors moving from in that direction from 0 to this point. And what is the image of a circle under a linear transformation? And of course, it's an ellipse. And then, of course, you can start studying it. This is not a symmetric one. So it's not at the point where you have the main axis here. You will be at the main axis of the ellipse and so on. So, but the main point is this is a dynamic thing. You can say, I would like to do a tangent, which might mean you're saying I'm going from here to here, from the center of the circle to the point. Then I make a connection, then I make it through the point, something which is orthogonal. And then I can say, well, now I'm taking the image of the tangent, and it will be the tangent to the ellipse. So this was actually a bachelor thesis that I was giving out for a student nowadays. So GeoGebra has not only an illustration reason, but it's also is very good to demonstrate dynamically. I think that this is a good point to stop here. And thank you for your attention. And actually, I will stop the recording now if I find the button.
Yeah, thank you very much, Professor Hans.
Yeah,
very nice lecture. I think surely this will enhance